Right, in this section I am going to speak about the different boundary conditions in the Monte Carlo method and how to handle such boundary conditions in different applications. Okay, so the boundary conditions. The governing equation is the Laplace equation or the Poisson equation or the heat equation with the source term. We have, generally speaking, we have three types of boundary conditions in different physical or mathematical applications. The first type of boundary condition is the absorbing boundary condition, or in mathematical framework, the Dirichlet or the first type boundary condition. In this type, I give you the magnitude of the unknown parameter, such as temperature here, on the boundary. So T is constant, this is the other name of this type. The first type is the absorbing boundary condition. The title shows that the random walker, which strikes the first type boundary, is absorbed by the boundary. So we call it the absorbing boundary condition, and the process of the random walk process will terminate when the random walker strikes this type of boundary. The other one is the second type is the reflecting boundary condition or the Newman type boundary. In this category, we have to give you the magnitude of the derivative of the unknown parameter on the boundary. So Q here is the heat flux, which based on the Fourier's law is minus K, conductivity, partial derivative of temperature with respect to the normal direction of the wall is constant. Because K is a constant, means that in this type we have the derivative of the temperature is none. The other name based on the Monte Carlo concept is the reflecting boundary condition, because the random walker which reaches the wall will reflect back or bounce back again towards the internal nodes. So the name or the title of the second category is the reflecting boundary condition. And the third one, which is partially reflecting boundary condition, or the rubbing type, or the third type boundary condition. As you see in this category, you will have a combination of the temperature itself and its derivative on the wall. Here, this is the heat flux, and this is the Newton's cooling law. This is the conservation of energy on the wall. So as you see here, we have K, H, and T sub infinity, and all of them are non-value parameters, and this equality constructs a relation between the magnitude of temperature and its derivative on the wall. So this is the partially reflecting boundary or the rubbing type. But this was a brief introduction to three types of boundary conditions. For example, consider that this wavy line here is the wall or the boundary of the domain, and the boundary is the reflecting boundary. Or for example, if Q equals 0, it means that the wall is adiabatic or isolated. So this is, as you see, the derivative of temperature with respect to x. X is the normal direction to wall. So in this example, it's horizontal. And the derivative is 0, it means that this is an isolated wall or adiabatic wall. And again, we have our grid points. The central node here is located on the wall. And the right node I plus 1j, the left node I minus 1j, and upper and under lower walls. As you see, this section is contributed to the fixed step Monte Carlo method. In variable step Monte Carlo method, the step changes, and we present some other modifications to this method to encounter different types of boundary conditions. Okay, so we have a fixed step grid points, and the central point is located on an adiabatic wall. In such cases, this is an example. you have to discretize the boundary condition. As you know, at the first step of the fixed step Monte Carlo method, we have to discretize the governing equation. Here you have to discretize the boundary conditions as well. Here the boundary condition is this relation, the derivative is 0, so you have to discretize it using the central difference concept. It results that the temperature of the right node should be equal to the temperature of the left neighboring node, these 2 points. But as you see, we don't have this point in real physical system because this is the wall and this is our material. So the I+1j is the virtual node or the ghost node, which will be eliminated in our future relations. Okay, and then substitute this relation into the discretized form of the governing equation and omit the temperature of the ghost node, which is Ti sub I plus j. And you will obtain a new governing equation which only 3 temperatures of the upper, the lower, and the left node in our case, just these temperatures exist in the governing equation, and then you can continue the random walk process. But when you reach this node on the wall, you will continue the process with a new relation just for this node. So this is a reflecting boundary condition because the random walker which hits this wall will come back, will go back through in the internal nodes, but just for the process at the wall, you have to use a new or another modified form of the discretized equation. So as I said, the P is the probability of motion of the random walker from node ij to node I plus j. The coefficient is 0, so the probability is 0. But the probability of P sub x minus changes in comparison to the probability for internal nodes. A coefficient here appears a factor 2. So Px minus is twice Px minus for internal nodes.